Hello, and welcome to this series about sugar beet processing. In this video, we will start at the beginning and focus on the technological quality of beets. We will see the definition of the technological quality of beet. What are the factors that impact it? And how will we assess it? The first thing I heard when I began my career in this exciting profession was, sugar is made in the field, not in the factory. Also, sugar technologists often use an old statement regarding a sugar factory's goal: the sugar factory does not make sugar, it separates non-sugars. This obviously does not minimize the important job expected of manufacturers, which is to maximize sugar yield and reduce production costs. As is well known, sugar technology is a separation technology. The separation of essential components or groups of elements in the main process steps of extraction, juice purification, evaporation, and crystallization in sugar manufacture are graphically shown in Figures 1 and 2. In Figure 2, the water content is not shown in order to highlight the distribution of the other beet components from one process step to the other. In the extraction step, insoluble non-sucrose substances are separated in form of pressed pulp. In the subsequent juice purification step, a part of the soluble non-sucrose substances are separated with the carbonation lime. In the evaporation step, most of the water is removed before thick juice is separated into the trading goods white sugar and molasses in the crystallization step. In each of these steps there are certain losses. Sucrose remaining in the beet pulp after extraction, known sugar losses. Sucrose losses caused by activity of microorganisms, unknown sugar losses, sucrose losses in carbonatation lime and, finally, sucrose losses in the molasses. We will see three cases. It is assumed that in all three cases, we have beets with the same sugar content of 17%. The sugar factory controls its processing parameters and achieves total sugar losses of 0.6% on beets and molasses purity of 58%. In the first case, the sugar factory extracts from beet thick juice with a purity of 95% and thus achieves a sugar yield of 89%, a recoverable sugar of 15% on beet, a molasses sugar of 1.2% on beets, and a molasses quantity of 2.6% beets. In the second case, the factory extracts thick juice with a purity of 90% from the beet. This gives a sugar yield of 90%, a recoverable sugar of about 14% on beet, a molasses sugar of 2.5% on beet, and a molasses quantity of 5.4% on beet. In the last case, we have a thick juice purity of 86% and the sugar factory achieves a sugar yield of 75%, a recoverable sugar of 12.7% on beet, molasses sugar of 3.7% on beet, and a molasses quantity of 7.9% on beet. So we see three cases and three different performances despite the process parameters being controlled. So the stakes are really high. What is the reason for this difference? Well, this difference is due to the beet technological quality, and mainly to the nature and content of non-sugars, and this is what we will see during this video. First of all, we will start by going back in history and living together the genesis of the beet sugar extraction industry. It all began in 1745, when the German chemist Andreas Markgraf proved that beet sugar and cane sugar were identical, and then wrote a memoir about the chemical experiments that made the extraction of beet sugar possible. His disciple, Professor Ricard, continued his work and succeeded in 1802 in building the first experimental beet sugar factory in the world, and which at the time produced 2 kilograms of sugar per day from 70 kilograms of beets. Ricard's work soon attracted the attention of Napoleon Bonaparte, who sent a commission to investigate the Ricard factory. And, faced with the British embargo and cane sugar deficiency, Napoleon ordered the creation of sugar schools and obliged farmers to plant a large area of beet. In 1811, Jean-Baptiste Querouel, a Frenchman working for the industrialist Benjamin Delizert, developed the refining process which finally made it possible to produce beet sugar on an industrial scale. For the first time, the impetus for the manufacture of this new sugar was definitively given and was presented in the form of a conical loaf in blue packaging. In 1812 Benjamin Delizert presented to the emperor perfectly successful sugar loaves, and that was the beginning of the blossoming of this industry. The sugar beet technological quality and its impact on sugar beet processing was already a matter of concern for several sugar technologists since the birth of this discipline. Thus Accard already recognized during his first attempts to make sugar from beet in 1803, that the sugar yield not only depended on the sugar content but also on the components hindering sugar manufacture, i.e. the non-sucrose substances in beet. Walkhoff, 1867, wrote, "A more exact value assessment requires that the entire chemical composition of the beet, i.e. the sugar content and the accompanying extraneous substances, be determined by scientific means in quality and quantity." Hersfeld, 1888, was probably one of the first authors to draw the attention of beet sugar manufacturers to the fact that root sugar content was not a sufficient criterion for judging the technical quality of a beet lot. But unfortunately, to date and in several countries, the sugar content in beet brine is still the only basis for the purchase price of beet. Dedick in 1958 wrote, "One must be able to express in numbers the characteristics which make up the technical value of the sugar beet. This requirement encounters several difficulties in practice." Winner in 1976 wrote also, "The technical quality of beet is determined by the sum of all properties of the beet delivered to the factory, which influence the extraction and yield of white sugar." Since then, much scientific work has been undertaken to identify the properties determining the quality of sugar beet and its juices, to elucidate their relative importance, and to express them in a simple formula, for example since 1960. So far, no generally accepted and binding solution of this problem has been found. In fact, what means the beet technological quality? Root quality is defined as a combination of all chemical, biological, and physical properties of the beet which affect sugar processing and decrease production costs. Thus, the parameters that determine the quality of the beet and its juice are three. First, there are the biological parameters in which we find the external constitution of beetroot, that is, the form of the root, fanginess, crown height, and other. Resistance to external influences. Bolting resistance and resistance to diseases. Variety and dependence on the environment. And finally, beet storage ability with the risks of respiration losses and infections. The chemical parameters include sugar content, non-sugar content and mark content. As for the physical properties, we note the ability to wash and slice cossets, and the elasticity and compressibility of cossets. Finally, the industrial parameters include extraction, filtration, and sedimentation capacity. Formation of coloring matter. Effective alkalinity value and others. Although root quality is defined as a combination of all chemical, biological, and physical properties of the beet which affect sugar processing, and decrease production costs, quality is usually used to describe the chemical composition of the roots. There are no quantitative criteria to assess physical properties of the roots such as slickability, elasticity, extractability, and pressability. Concerning the chemical composition of beet. Beetroot consists of 76% water, 4% insoluble compounds, and 20% soluble compounds. In these soluble compounds, we find sugar at around 17%, proteins at 0.4%, alpha-amino nitrogen at 0.25%, betaine at 0.2%, all the cations, and anions at 0.3%, pectic substances, saponins and glucose at 0.1%, fructose, raffinose at 0.05% and galactose at 0.01%. Of course, this composition can vary considerably depending on the variety and growing conditions of the beet. The total soluble non-sugars only represent about 2 to 3% of the beet weight, but it is their nature, content, and distribution that is decisive for sugar beet processing. Some of them are much more important than others, so we will classify them into 3 groups. In the first group, we will find all the non-sugars that will not be eliminated or that will be decomposed at the purification stage. These non-sugars represent about 6.4 grams % G sugar in the raw juice. In group 2, we find all the non-sugars that are partially eliminated at the purification stage. They represent 1.1 grams % G sugar of the raw juice, and finally in group 3, we find all the non-sugars that will be totally eliminated at the purification stage. They represent about 2.05 grams % G sugar of the raw juice. First of all, it can be seen that only 30 to 35% of these non-sugars will be eliminated during the purification process. Part of the 1.1 grams of group 2 and all of the 2.05 grams of group 3. Glutamine is partially decomposed in the purification process to pyroglutamic acid and ammonia. Similarly, the reducing sugars will be decomposed into acidic products and coloring substances. Thus, both the unreacted glutamine, the reducing sugars, pyroglutamic acid, and the degradation products of the reducing sugars will pass the purification stage and thus influence the rest of the process, especially the ion balance of the juice. Finally, it should be noted that this composition is subject to considerable variability depending on the growing conditions of the beet. Now we will see the impact of non-sugars on sugar beet processing. We have seen that the technical quality of beet depends on its composition. The sugar content is the most important parameter in quality assessment. However, the sugar extracted is influenced by several beet compounds. Among these compounds, there are the molassogenic compounds. These have the property of increasing the solubility of sucrose, thereby reducing crystallization, and finally increasing sugar in molasses. These compounds include potassium, sodium, amino acids, betaine, pyroglutamic acid, chlorides, sulfates, lactic acid, and nitrates. These molassogenic compounds are classified according to their molassogenic effect, i.e. the quantity of sugar retained per quantity of non-sugars. Thus, according to their molassogenic powers, we find compounds that are very molassogenic, moderately molassogenic, and slightly molassogenic. Among the non-sugars that impact beet processing, we have compounds that influence alkalinity. The alkalinity of the juice is negatively affected by the presence of amides and amino acids by ammonia fractionation. Also by reducing sugars that will decompose into acids during the purification stage. And finally, magnesium and calcium by precipitation. The acid anions contained in beet and passed into the raw juice during extraction, such as phosphate, oxalate, citrate, sulfate, and malate form, in reaction with calcium hydroxide, in part sparingly soluble, precipitates which hence are eliminated and thus provide alkalinity. If the alkalinity consumers in the juices, mainly amino acids and invert sugar with its metabolites, exceed the alkalinity producers, mainly potassium and sodium, the alkalinity reserve of the juices is too low to keep the pH stable. In that case, it may be necessary to add soda during juice purification to increase the thermostability of the juices and avoid color formation during evaporation. As we have seen, soda is highly molassogenic, which unfortunately results in an increase in molasses sugar. Among the non-sugars that impact beet processing, there are compounds that are optically active. Their presence increases the apparent concentration of sugar in any solution measured by polarimetry, for example raffinose, dextran, and amino acids. To understand this aspect, we will look at the principle of polarimetry developed in 1911 by François Arago. A polarimeter consists of a light source, a fixed polarizer, a polarimetric tube that represents the sampler cell, and a rotating polarizer. The principle is the following: the light source will emit an unpolarized light. This unpolarized light will become polarized by passing through the fixed or linearly polarizer. And then, it will enter the sample cell, which contains an optically active substance. These optically active molecules rotate the plane of polarized light due to their optical activity. When the light exits the cell, the plane polarized light is not the same as that of the incoming polarized light. The analyzing rotator prism is fixed in such a way that it can be rotated easily about the axis of the incident light. It is used to measure the rotatory power or angle of rotation of a particular optically active compound. When the molecule present on the sample cell rotates the plane polarized light in the clockwise direction, we called it dextrorotatory rotation. However, the molecules rotate the light counterclockwise, we call it levorotatory rotation. Each optically active substance has its own specific rotation as defined in Bio's law. The rotational power or the angle of rotation of the plane of polarization of the solution is equal to the specific rotation of the dissolved active substance, which is a function of the wavelength of the light used multiplied by optical path length, multiplied by the mass concentration of the active substance. In the particular case of the sugar industry, polarimeters are called saccharimeters. ICOMSA, the International Commission for Uniform Methods of Sugar Analysis, has defined a saccharimetric scale graduated in international sugar degrees. The 0 degrees Z point is fixed by the indication given by the saccharimeter for pure water. The 100 degrees Z point of the International Sugar Scale is fixed by the optical rotation alpha undergone by the polarized light of the green line of the mercury isotope 198, lambda equals 546.2271 nanometers in vacuum, when passing through a 200.000 mm length of sucrose solution in pure water, kept at a temperature of 20.00 degrees Celsius, and containing 26.0160 grams of pure sucrose weighed in vacuum per 100.000 cubic centimeters of solution, normal sugar solution. In the given conditions, 100 degrees sugar corresponds to an angle of optical rotation of 40 degrees. For the yellow sodium light that is widely used in saccharimeters, 100 degrees sugar corresponds to an angle of optical rotation of 34 degrees. And of course, in the range from 0 degrees Z to 100 degrees Z, the scale graduation is linear because the optical rotation is practically proportional to the sucrose concentration of the solution. According to Bio's law, for the case of normal sugar solution, we can calculate the specific rotation of sucrose. The angle of rotation of 34 degrees, for the length of 200 mm and for the concentration of 26 grams per 100 milliliters, the specific rotation of sucrose is 66.54 degrees. Now, we will see the specific rotation of some constituents of beetroot. So for the group of monosaccharides, glucose has a specific rotation of plus 52.5 degrees, fructose minus 92.4 degrees. Sucrose, as we have seen, has a specific rotation of plus 66.5 degrees. Raffinose has almost twice the rotation of sucrose, 123 degrees. Galactanol 136 degrees, and the kestose, depending on their form, have a specific rotation of between plus 26 and minus 47 degrees. For polysaccharides, dextran has a specific rotatory power of 200 degrees, 11 minus 40 degrees. Concerning amino acids, their specific rotatory varies according to their nature. Finally, we will look at the compounds that affect the color of the juice. Color is an important criterion for the quality of white sugar. First of all, there is the degradation of reducing sugars during purification, which forms colorants. In addition, The presence of reducing sugars with amino acids, mainly glutamine, will form melanoidins in the Maillard reaction, and thus impact on coloring. Thus, it is clear that a high concentration of non-sugars will always lead to high demand for processing aids and energy, in addition to the lower sugar yield. Now we will look at the technological quality sugar beet assessment. Several formulas have been developed to evaluate the impact of beet quality on beet processing. The criteria used in the evaluation of quality are molasses sugar, i.e. the sugar remaining in the molasses. It is expressed as a function of the beet sugar content, the total losses, and the purity of the thick juice and the molasses, according to the following formula. The recoverable sugar is equal to the beet sugar content, minus the sugar in molasses and the total sugar losses. Then the sugar yield is the recoverable sugar % beet sugar content. Finally, the total losses are generally considered constant and are estimated at 0.6% of the beet. The recoverable sugar, as Dedick pointed out, establishes a relationship between the chemical composition of the beet and their technical value, and thereby provides a benchmark for beet quality assessment. We will see two cases of beet quality. A first case where we have a good quality beet characterized by a thick juice purity of 95%. In this case, we will have a recoverable sugar of 15%, a sugar yield of 89.5%, and a molasses sugar of 1.19%. In the second case, we have a poor quality beet characterized by a thick juice purity of 88%. Under the same conditions, we have 13% of recoverable sugar, a sugar yield of 78%, and molasses sugar of 3%. There is an increase in molasses sugar of 2%. In order to calculate the extracted sugar, it would first be necessary to calculate the molasses sugar. Therefore, several studies have been carried out to relate the different molasses compounds in beet to molasses sugar with multiple regressions depending on potassium, sodium, alpha-amino-nitrogen, and other residual non-sugars. Dedick in 1927 assumed that 1 millimole of potassium plus sodium will retain 1 millimole of sugar in molasses. Knowing that the molar mass of sucrose is 342 grams per mole, molasses sugar is then equal to 0.342 multiplied by the sum of potassium and sodium. Sodium and potassium are expressed in millimoles per cent grams of beet. Reinefeld in 1974 calculated molasses sugar values from 58 thick juice analyses and correlated them with the corresponding beet analysis results. This calculation gave the following equations: molasses sugar and recoverable sugar. There is a multitude of formulae that estimate molasses sugar according to the molassogenic elements in different countries, and sometimes even several formulae have been established in the same country. For the Czech Republic, molasses sugar is a function of sodium and potassium. For Austria, the formula established in 1971 introduced the so-called alkalinity factor, which is equal to sodium plus potassium on the alpha-amino-nitrogen, and there are two different formulas depending on the value of this factor. In the same country, Austria, another formula was established in 1996, which estimates molasses sugar according to potassium, sodium, alpha-amino-nitrogen, and reducing sugars. For the Netherlands, the alkalinity factor has also been introduced, and there are two different formulas depending on the value of this factor. For Germany, the formula established in 1974 estimates molasses sugar in terms of potassium, sodium, and alpha-amino-nitrogen. In the same country, another formula was established in 1993, expressing molasses sugar in terms of potassium, sodium, alpha-amino-nitrogen, betaine, and raffinose. In Germany, another formula was established in 1995, and this is the official formula, which estimates molasses sugar in terms of potassium, sodium, and alpha-amino-nitrogen. For Hungary, molasses sugar is a function of potassium, sodium, alpha-amino-nitrogen, and reducing sugars. In Ukraine, molasses sugar is a function of potassium and sodium. In Turkey, molasses sugar is a function of potassium, sodium, alpha-amino nitrogen, and reducing sugars. In Morocco, molasses sugar is a function of potassium, sodium, and alpha-amino nitrogen. In France, molasses sugar is a function of potassium, sodium, alpha-amino nitrogen, and glucose. In Spain, molasses sugar is a function of potassium, sodium, alpha-amino nitrogen, and reducing sugars. Therefore, it can be seen that there are no fixed and unique formulas for estimating molasses sugar, so it depends mainly on the growing conditions of the beet. So what are the factors that affect beet quality? Actually, there are several varietals, environmental and agronomic factors that influence beet quality. First of all, there are the climatic conditions. Drought and high temperatures during growth also have adverse effects on root quality, raising levels of individual amino acids, other nitrogen compounds, and inverting sugar. In this regard, the difference between the qualities of Northern European beet and Mediterranean beet needs to be mentioned, as shown in this table. In addition to the decrease in quality due to the formation of high levels of reducing sugars due to high temperatures during harvest, Mediterranean beets have higher levels of sodium and alpha-amino nitrogen. Another key climatic factor with respect to beet quality is undoubtedly frost and the often irregular timing of its occurrence. The second factor affecting beet quality is a varietal choice. The varietal choice is one of the most important factors that impact beet yield and quality. There are three main types of varieties. First of all, there is the E-type variety, which comes from the German Urtra Greek, i.e. rich in yield. This variety produces beets with a high root weight, on average 900 grams, but with a low sugar content of 14% to 15%. The second type is the Z-type, from the German Zuckerreich, which means rich in sugar. This variety produces beets with a high sugar content of between 17% and 18%, and small conical roots with an average weight of 600 grams. Finally, there is the N-type variety, from the German Normalreich, i.e. normally rich. This variety produces beets with medium sugar content and roots. The varietal variation between these three types C, Z, and N is continuous. Varieties that belong more or less clearly to one of these types are often intermediate. They are then characterized by two letters, EE, very low sugar content type, Ni, NZ, and ZZ, very high sugar content type. There are therefore many varieties. The main selection criteria are root yield, sugar yield, the quality of the extracted juice, i.e. its purity, the nature and quantity of the non-sugars that make it up, tolerance to certain diseases and parasites, resistance to bolting, tolerance to drought stress, and finally, the reduction of dirt tear according to the shape of the root. Such roots tend to have shallower root furrows and a smoother skin, characteristics that give a lower dirt tear and make washing easier. Genetic progress is thus an essential lever for increasing the competitiveness of the beet industry. Although beet yields seem to have stagnated in many regions over the last 10 years, varietal selection can offset the large part of the losses related to climate change and increased pressure from pests. Genetics, therefore, remains the only answer to certain diseases and parasites. The third important factor affecting beet quality is nitrogen fertilization. Nitrogen is the nutrient with the greatest influence on sugar beet yield. Nitrogen is a key component of enzymes, vitamins, chlorophyll, and other cell constituents, which are essential for crop growth and development. However, if too much nitrogen is applied, there will be a reduction in sugar concentrations and an increase in impurities. This graph shows the evolution of root yields and the evolution of beet sugar content as a function of the nitrogen dose applied. It can be seen that the application of nitrogen increases the yield, but reduces the sugar content. The second graph shows the evolution of sugar content, sugar yield per hectare, and alpha-amino nitrogen concentration as a function of the nitrogen dose applied. It can be seen that the higher the applied nitrogen dose, the lower the sugar content, the higher the alpha-amino nitrogen content, and the lower the sugar extract per hectare. This study shows the effect of increasing nitrogen rate on amino N content leading to a reduction in sugar yield. Thus, an adequate supply of nitrogen is essential for optimum yield, while excessive use may result in an increase in roots with lower sucrose content and juice purity. The graph shows the relationship between fertilizer nitrogen rate, amino N content, and extractable sugar yield. It can be seen that increasing nitrogen doses increase the alpha-amino nitrogen content, and the sugar yield passes through an optimum. The last graph shows the evolution of the root yield per hectare, and the sugar yield per hectare, as a function of the fertilizer nitrogen rate. It can be seen that the optimum nitrogen rate for extractable sugar is lower than the optimum rate for beet yield. Thus, the optimum supply of nitrogen depends on the growing conditions, soil type, previous crop residues, nitrogen from organic manure, etc. Therefore, only a provisional nitrogen balance allows the optimal dose of nitrogen to be applied. In this graph, we can see the evolution of the fertilizer nitrogen rate in Great Britain between 1955 and 1995. So we can see the decrease in the fertilizer nitrogen rate during those years. Between 1977 and 2012, the dose of nitrogen applied in France fell from 176 kg per hectare to 85 kg per hectare in 2012. The sugar purchased in tons per hectare increased from 8.1 tons per hectare to 13.4 tons per hectare. We can also see that the nitrogen dose goes from 21.7 kilograms of nitrogen per ton of sugar to 6.3 kilograms per ton of sugar. Thus, in 30 years, the consumption of nitrogen per ton of sugar has been divided by 3.5 in France. In 30 years, the nitrogen fertilization rate in Great Britain has also been reduced by 60 kilograms per hectare, and in Germany in 2018, it has been reduced to 8.7 kilograms of nitrogen per ton of sugar. Finally, to conclude with the nitrogen fertilization, we can see on this graph the evolution of the beet sugar content and thick juice purity according to the fertilizer nitrogen rate. We can see that the higher the fertilizer nitrogen rate, the lower the sugar content and thick juice purity. Another factor that affects the beet quality is the technical management of the crop. In this section, we note the importance of crop rotation, soil preparation, plant density, weed control, and irrigation. Another very important factor affecting beet quality is diseases and pest attacks during beet growth. So all important sugar beet diseases decrease root yield and sugar concentration, too. Most of these effects are controlled by the use of tolerant varieties as in the case of Rhizomania and Cercospora. However, root rots are very difficult to control and can seriously affect root quality. Thus, because of the sugar loss and the changes in plant metabolism, the concentration of non-sugars increases. However, the most severe alteration is the hydrolysis of sucrose into invert sugar, which can increase up to 100 millimoles/kg. We see here an example of a Rhizoctonia attack. In this table, we have two lines. In the first line, we have beets that are not infested, and in the second line, beets infested by Rhizoctonia. So we see a decrease in beet sugar content, but above all, a phenomenal increase in reducing sugars. We go from almost 3 millimoles per kilogram to 83 millimoles per kilogram of beet. In the case of a soft rot attack, the damage is much more serious. Since the presence of rotten roots next to healthy roots reduces considerably extraction performance. Here we will see an example of an attack by Sclerotium rolfsii. In this graph, we can see the influence of the proportion of root rot on the quality of the raw juice, and in particular reducing sugar's content. It is clear that when the proportion of root rot increases, the reducing sugar content of the raw juice also increases. The same observation can be made in this graph, which shows the impact of root rot at different proportions on sugar losses % on beet. For example, with 1% of root rot presence, we have 3% beet of sugar losses. So, the presence of root rots, even in small proportions, has a considerable impact on beet processing. Therefore, the only solution to this problem is to sort out the rotten roots and avoid receiving them. Another factor affecting sugar beet quality is drought stress. So drought stress, probably in combination with heat stress, is one of the major constraints to sugar beet production worldwide and is the most important environmental factor affecting sugar beet yield and quality. Thus, in the face of drought stress, the concentration of dry matter will increase. As all substances in the beet are expressed on a fresh matter basis, the sugar and mark concentration may increase, too, but on a dry matter basis, sugar is reduced markedly as the composition of the dry matter shifts. Beets grown in Eastern and Southern Europe often show these qualities with enhanced concentrations of sodium, amino N, and especially invert sugar. So to conclude, the beet technological quality is a crucial parameter that impacts considerably beet processing. In Europe, considerable progress has been made in improving the beet quality. Here we see the example of the Netherlands in two graphs. In the first one, we can see that between 1981 and 2013, the root yield increased significantly and the sugar yield per hectare increased from 8 tons per hectare in 1980 to 14 tons per hectare in 2013. The second graph shows the evolution of thick juice purity between 1980 and 2013, which rose from 92 to 95%. The same observation can be made in Belgium through this graph, which traces the evolution of thick juice purity between 1990 and 2003. This is a clear example of the progress made in the beet quality. The thick juice purity went from 92.4 in 1990 to an average of 95 in 2003. This represents an average increase of 0.23 units per campaign. Today's thick juice purities are significantly higher than the standard liquor purity of the early 1990s. Thus, the logical consequence of this quality improvement is a clear increase in productivity, a significant decrease in molasses sugar, and a higher white sugar yield per ton of beet. Finally, how can the beet technological quality be monitored and evaluated in a practical way? It should be noted that when beets are subjected to biotic and abiotic stresses, such as prolonged storage, pest attack, or diseases, such as root rot, defoliation, or drought stress, the beet defense mechanisms will automatically be activated, and the result will be an increase in reducing sugar's content. Thus, monitoring reducing sugars is essential to better determine the beet technological quality. This is why the systematic analysis of beet reducing sugars content at the beet reception laboratory will help detect the incriminated plots in case of an abnormal increase, diagnose the reasons for this increase, and thus take the necessary measures for a possible correction. I would like to remind you that the normal total reducing sugar content of fresh beet is generally between 0.2 and 0.6 grams of sugar or 0.02 and 0.08 grams of beet. Another way of monitoring and assessing the beet technological quality at the control laboratory of the sugar factory is to monitor the quality of the Cosset press juice and the effective alkalinity of the clear juice. In fact, for a good quality beet, it is necessary to have a press juice purity higher than 90%, a press juice reducing sugar's content lower than 0.6 grams% Brix, a press juice lactic acid content lower than 50 mg per liter and effective alkalinity of the juice higher than 0.01 grams of cow per liter. Here you will find the various bibliographic references used to prepare this video. That is the end of this video. I hope to contribute to the understanding and popularization of this topic. Don't forget to subscribe to the channel to stay informed of the latest news. And also, if you haven't already done so, download the free tool for calculating the parameters of the beet sugar processing from Play Store. That's all for the moment. Thank you for your attention, and see you soon.